Okay, for this video we'll be using conservation of total energy to solve for this kinetics of particle problem. So in this question we have over here it states the spring of constant K is unstretched when the slider of mass M passes position B. If the slider is released from rest in position A, determine its speed as it passes point B and C, and what's the normal force exerted by the guide on the slider at position C. So I'll just neglect the friction between the mass and the circular guide. Okay, so now we know that through conservation of energy, we know that energy must conserve at all stages during this movement. Okay, so movement. So that means energy at state A, total energy at state A must be equal to total energy at state B and equals to total energy at state C. So for now, I'll take total energy of state A is equals to this is my zero reference point, so that's the height lah. So zero height, and then over here it's height R and height 2R. So energy at state A, we have mg2r, so that's the gravitational and potential energy, plus half mv squared, which goes to 0 because it's released from rest. So rest velocity is 0, plus half kx squared. K is the K constant of the spring, x is the change in length. Okay, so that's energy of A. Now we write down equation of energy of B. So when you reaches stage B, you have mgr, gravitational potential energy, some form of velocity. So v1 will be the velocity at point B, and half kx squared, because we know that once it passes, when it slides to B, right, then it would have no more it will be unstretched already once it reaches B. So it's over here. So there will be no elastic potential energy. Alright, then we write down what's the energy at C. At energy of C, there's no gravitational potential energy, there's no elastic potential energy, so there's only kinetic energy. Alright, next we'll find what's change in length x, and that is square root 2r minus r. Why is it square root 2r? Because A to B is r, this central point to B is also r, so the length of this point to A is square root 2r. Okay, through Pythagoras theorem, square root 2r, then minus r when it's not stretched at all, so that's the delta in x. Okay, now through conservation of energy, we equate energy at state A equals energy at state B. So I just bring this equation down here and this equation down here. Very simply, through manipulation of equation, we can express in terms of v1, which is the velocity at state B, and this is the answer. Okay, so quite simple. Next, to find the velocity at state C, I'll equate energy at state A equals energy at state C. So simply, energy of state A is over here, so I'll take this whole chunk and place it here. Energy of state C is here, kinetic energy, and bring it down over here. Okay, so very simply, I express everything in terms of V2, and then I'll get my answer. To find the normal force that's acting on C, we can use the kinetic diagram and free body diagram. So on my left there's free body diagram, on the right is kinetic diagram. Okay, to be more accurate, kinetic diagram has a mass multiplied to this acceleration, but you still get what I'm trying to say lah. Okay, so through Newton's second law, summation force equals to mass times acceleration. We take upwards as positive, so normal force minus the weight of this particle C equals to mass times acceleration. So acceleration, we know that during this movement of this circular path, there is normal and tangential acceleration. We do not care about tangential acceleration because we just want to find along this y-axis. So to find centripetal acceleration, it's v squared over r. Alright, so through so I'll simplify this whole equation, and then I can very simply get the answer of the normal force. Okay, so that's the answer.